Okay. Welcome to this session in which we will discuss Java in containers. So first of all, I want to say that it's great to be back. So in fact, I was at Jfokus in 2017, same room, same stage. And back then, so I did a presentation, and back then someone in the audience tweeted that it's not a real conference unless you read Oracle's safe harbor statement at least once. So here it is. Please enjoy. So my name is Delabassee. Despite my French accent, I'm not French, but I'm from the French-speaking side of Belgium, where I work for Oracle. So I'm part of the Java platform group, so basically the group that is responsible for Java, the platform, and OpenJDK. I'm remote, so I live in Belgium, but I report to the organization in the States, in California. And if you have any questions, or if you want to do any follow-up, you can reach me on Twitter, or you can try to grab me during the next 2 days. Something else. Apple has recently launched a new MacBook with a new keyboard. Why I'm telling you that? Well, unfortunately, I have the old models with the broken keyboard. So today I'm going to do a few demos. If any of my demo fail, it's not my fault, it's the keyboard. Not only that, this is also a subtle message to my manager. OK, before we talk about Java into containers, and first I have to mention, so first that talk was Java into containers, but then I turned that into JVM into containers, because at the end of the day, it's really about how to make sure that a Java virtual machine runs well and correctly within a containers. At the end of the day, a JVM only understands bytecode. Most of the time, that bytecode is coming from a Javac compilers, but if it comes from another compiler, it will provide the exact same behavior. So it's really about making sure to run the JVM correctly within the containers. So containers, so who's using containers today, by show of hands? So yes, that's what I've guessed. So I wouldn't spend too much time on explaining what a container is. As a recap, it's basically a way to package software and its dependency into a unit that we can easily move around. Very convenient for development, but also for deployment, for testing, and so on. There are multiple containers runtimes. At the end of the day, what I'm going to discuss today applies to Linux containers runtime that are based on C groups and namespace. So containers are leveraging some of the Linux kernel facilities, such as C group, namespace, also union file systems, and so on. Whatever we're going to discuss today applies to any container runtime that is using C groups and namespace. I'm going to use Docker for my demo, but it will also work with different runtimes. So we shouldn't confuse containers with virtual machines. Containers are using C groups and namespace for the operating systems, but one drawback of containers is the isolation level that they provide. So we have some form of isolation, but clearly the isolation is not that great. Why? Because basically we are running and we are sharing the same host operating systems. So everything runs on the same host operating system. On the other hand, we have virtual machines that use technologies such as an hypervisor to provide a stronger isolation. And then we can have different operating systems within the VM that we have on the host itself. There is now what we call kata container, because one of the benefits of VM is basically the isolation that we have, but one of the drawbacks is the cost. Starting a VM is very expensive. Kata containers basically brings the benefit of the two. So we have almost the startup time that we can have with containers, but we have the isolation that we have with VMs. So basically it works with a lightweight VM, and then we have containers on top of that. So let's now switch gear and talk about Java. So obviously, containers are widely used in the Java space too, because of multiple reasons. The cloud is one of them. And if we look at the landscape of our toolings, well, you see that all the tools in the Java space are evolving to support containers. So we have multiple Maven plugins that we can use to easily create a container image. There's Jeep from Google that we can also use to create container image. Test container. IDE also those days support the ability to directly create containers out of the IDE itself. If you look in the microservices space, most of the frameworks support out-of-the-box containers. So look at Helidon, Quarkus, Gypsers, and so on. You basically build your artifact, and you can directly turn that into a containers. The serverless space is also heavily relying on containers. that's true for the Java space, but also the serverless space at large. So whatever we're going to discuss today apply to all that space at large. So what do we want from a JVM that runs within the containers? Basically, there are two things that we need to tackle. First, we want to make sure that the JVMs behaves correctly when it runs within the containers. And we'll see why it's important. Then there's the question about making sure that we have a good latency. By latency, I mean, whenever we start a container, we want to make sure that the Java code that runs inside starts as quickly as we can. Because containers tend to be disposable. So containers are easy to build, they are easy to ship around. So we're going to tend to use a lot of containers. So obviously, we don't want to have to wait like for a VM minutes for that container to start. So that whole latency question is something that is very important within that space. So I'm going to first start with a very basic demo. So it's really the hello world of containers. So for that, I'm going to switch to a Unix VM, and prox that has 8 CPU. So I have, let's see. So this is a basic hello world application that basically look around at some of the system properties. So which version am I using, which Java vendor that JVM comes from, am I running within the containers, and so on and so on. Then we have a Docker file to containerize that. Yeah, it's, so let's, sorry, nano. Sorry. And I'm going to use, for example, this one. So the Docker file is pretty basic. So I start from a base image, java-latest. I create a directory. I copy my source. I compile it, and I run it. So let's build that. So build -t. Let's call it rn. And this is our context. No, sorry, I'm not in the right directory, and my context will be too big. So yeah, that one is good. So docker build, -t, and this is our context. Let's run that. So it's run. So hello world, here is what I see. So this is a quite old version of Java. It comes from Oracle. I'm indeed running inside the containers. I have 8 CPU. So the JVM sees 8 CPU, so it will configure accordingly 7 threads for the command for join pool. And it's going to use that much memory. So we can already see, if we do this, Docker run image. So the size for that very basic application is over 600 megabytes. This is already a big issue. This is a pretty basic code that basically just displays some information, and for that, we need to fetch an image that weighs over 600 megabytes. And why this is an issue? Well, each time we need to run that code, basically the container runtime will have to pull that from a registry. Obviously, ideally, the registry will be co-located on the network, on the same network, but still, to just display some information, the container runtime will have to fetch over 600 megabytes. So we're going to see how we can work around those issues a bit later. So back to the slides. So latency. Basically, there are 2 levels on which we can work when it comes to latency. First, there is the time it takes to start up the container, and then there's the time it takes to start the containerized code. So basically, the Java application, the JVM, and the Java application. So there are 2 levels on which we can work on. The container startup, well, as I alluded, we need to make sure that our container is as small as possible. Our container image should be as small as possible. So you know that container is basically a stack of images, and we need to make sure that basically each layer is as small as possible. When it comes to Java application, there are 3 types of layer. There's the Java top to bottom, there is the Java runtime layer that include the Java application and its code. Then there's the Java runtime, that's basically the Java virtual machine. And then below that, we have the operating system layer that will host our JVM. So we basically need to make sure that we shrink as much as we can those layers. So if we look at the Java application layers, basically the thing that we can, there's not much that we can do. I mean, we can give you advice and best practices. Typically, watch out the dependency that you are using. Don't bring any transitive dependency that are not needed, those kind of things. It's also a good idea to try to leverage some of the cache mechanism that we have in the containers. And that's why fat jar are maybe not a good idea. Try to basically have different layers when it's possible. And that way, you will leverage the cache, and only the layers that will be updated. So you don't have to pull all the layers again and again. But still, there are technology on the Java side that can also help us, like CDS, class data sharing, that we're going to discuss a bit later on. Now, at the Java runtime layer, there are things that we can do to reduce the size of that layers. And what we can do is use jlink that has been introduced in Java SE9. So part of the modularity, we have these jlink tools that give us the ability to create a custom runtime image that will only include the module that our code needs. So our application will have a runtime with just the capacity, the feature from Java that is needed by the code. To give you some sense of the benefit that we can get by using jlink, I started from a serverless Java function running on FN with OpenJDK 13. So first, we start from a whole JDK. A whole JDK 13 weight 316 megabytes. It's not a good idea to run Java application to run them on top of a JDK. Why? Because basically, you want, from a security point of view, to reduce the potential surface attack as much as possible. So it's kind of stupid to carry a Javac compiler within your runtime image, because we know that at runtime we won't need a Javac compiler, and so on and so on. So we need to use a GRE instead of a JDK. The thing is that since Java 8, there's no, since Java 9, there's no GRE anymore. So that's one thing. But on the other hand, we can use jlink to basically create our custom runtime image. That would be kind of a custom GRE. If we do that, so that's what I did next. So I basically created a custom runtime with all the modules. We go from 316 megabytes to 178 megabytes. So that's a huge win on one hand. On the other hand, it's very stupid to create a runtime image that includes all the modules, because there is no way your code can use all the modules from the platform. So what I did next, I used jlink as it was designed to be used. I basically created a runtime that only includes the modules that my serverless Java function needs. So for that, I've used JDEPs to get the dependency. And I went from 168 megabytes to 50 megabytes. So 50 megabytes, that's basically a complete Java runtime to run my serverless Java function. We can remove, using jlink, some information that is not needed, like header files, man page, and we can also strip out some debug information. If we do that, from 50 megabytes, we will go down to 44 megabytes. In jlink, we have two levels of compression. If we do that, level 2 is basically zip deflate. We'll go from 44 megabytes to 34 megabytes. So basically, by using jlink, we can go from a whole JDK that weighs over 300 megabytes to a custom Java runtime that, in this case, only weighs 34 megabytes. Now, something to mention. We did that to basically reduce as much as we can the size of the Java runtime layers. If you look at the bottom of the tables, I'm using compression. If I'm compressing stuff, I will have to decompress them. Maybe the benefit that we will get by saving a few megabytes there is something that we will lose when we will have to decompress stuff. So we should maybe stop at 50 or 44 megabytes, and we're good with that. That's something that you would have basically to measure. So using jlink is something that we can use to shrink the Java runtime. Now, what about the operating system layer? Well, there are multiple things that we can do. The first obvious things to do is to use a slim distro. And watch out, it's not because there is slim in the distro name that it's slim. So that's something that you need to look at. So using a slim distro is one thing. We can also rely on distroless distro. So that's a Google effort. And The Java 11 distro from Google weighs 189 megabytes. That's a lot, but that's basically the operating system and Java 11. So that's everything built in. So that's one thing that we can do. Something else that we can do is use different tools that mimify our Docker image, such as Docker Slim. Now, I put their claim between quotes because so they're claiming that they can mimify the image up to 30 times. The thing is that I've tried and it doesn't work, at least on my machine. So they are supposed to come with a new version that should solve my issue. So until then, I don't know. So that's one thing that we can do on the operating system layer. Something else that we can do is we can leverage lighter operating systems, such as Alpine. So Alpine is a security-oriented Linux distribution that weighs between 5 and 6 megabytes. So basically, in those 5 to 6 megabytes, you will have a full-blown distribution that you can use to run your code. Obviously, you will not have all the bell and whistle that you have from a typical distro, such as grep, package dependency management, and so on and so on. But at the end of the day, it's good because, again, within the container space, we want to reduce as much as we can the potential surface attack of our containers. The issue with Alpine is that it uses muscles. And OpenJDK rely on libc, jlibc. So jlibc is basically the library that the C++ code of hotspot of the JVM, because hotspot is written in C++. That's the library that it used to talk to the underlying operating system. So OpenJDK use libc, Alpine use a different one, which is muscles. So we can either use Alpine package glibc, which is an intermediate layer that will basically do the mediation between muscle call to, libc call to muscle calls. I'm not a big fan of that. Not only that, well, I find that solution a bit tricky, and also it had anyway weight to our image. So that's not, to me, that's not a good solution. Something else that we can use is Portola. So Project Portola is a project within the OpenJDK community whose goal is to build OpenJDK on top of muscles, so that you can run directly OpenJDK on top of muscles. Technically, so it works nice. The thing is that it's not, well, we don't do all the tests that we do with a typical OpenJDK distribution. So you can use it in distribution at your own, in production at your own risk, but ideally don't do that. That's why at this stage, so right now the current version of OpenJDK is 13, so we're giving the build for Portola on 14. And when 14 will be released, we will provide the build for Portola on 15, and so on and so on. Having said that, if you want to help us to port OpenJDK to muscles, contributions are welcome within the project Portola. So feel free to join and jump in and help us. So I will do a demo to illustrate that. And one of the comments that I had when I saw the result that I had when using jlink with serverless function is that, well, it's good, but it's a serverless function. What I'm using is a server. So what benefit would I get? Well, and that's true. So for this demo, I took a server. And for that, I'm basically using the Minecraft server. At the end of the day, it's a server that runs on the network, so we're good with that. So let's see. Let's go. So what I have is a Docker file that will containerize my Minecraft server. So you see that I'm starting from OpenJDK 14. Everything happened here. So here I'm using jlink to compress level 2, and basically I'm creating a custom Java runtime with all the modules and just the modules that Minecraft server needs. So here I specify by using the add module flags which modules are needed by the Minecraft server. So that's the first step. That's a multi-build multi-stage build. So this is the first stage. Then I start from a base image, an Alpine base image. I create a directory. I copy all the files that the Minecraft server needs, like the license, the properties file, and the jar. And then I copy my runtime, my custom runtime from the first stage, and I'm done. So let's build that. So build, I said, -t. That's the keyboard. I told you. Also, I'm going over my mobile phone, so that's why it might be a bit slow. OK. So I have this mine image. Now, we can already look at the size of that image. It weighs 100 megabytes. So in 100 megabytes, I have an operating system, I have a Java runtime, and I have my server application. We can have a look at exactly what we have inside. So for that, I'm going to use dive. OK, so on the left side, you have the layers, and on the right side, you have the content of the layers. So the first layer, the 5.5, is Alpine. So that's the operating system. That's the Linux operating system needed to run that code. Then we have 181 bytes. If we look there, that's basically the license. Next layer, property files, and next layer, the jar. It would have been a good idea to put those 3 files in a single layer, but. And then we have this 58 megabyte layers, which is my custom runtime. So it's basically my Java runtime with the 12 modules that are needed by my Minecraft server. And at the end of the day, I indeed have a complete Docker image that only weighs 100 megabytes. So whenever that container will have to be invoked, the container runtime will just have to fetch that 100 megabytes through the network. So Minecraft server, OpenJDK 13, 12 modules, 88 megabytes. If you strip debug, so if you strip the debug and the native debugs and the Java debugs attributes from that image, you will save 14 megabytes. If you use compress1, you will save from the 88 megabytes, you will save 18 megabytes. If you use compress2, from the 88 megabytes, you will save 31 megabytes. And if you remove the header file and the main page, you will not save anything because they are not included by default. So this is on using the OpenJDK latest. So OpenJDK latest Docker Hub image is based on OpenJDK, so the Oracle OpenJDK build that runs on Oracle Enterprise Linux. But if you are using other Linux distribution and other OpenJDK distribution, you might have different results, such as this one. So OpenJDK 13, a custom runtime image with 1 module weight 48 megabytes. So you will not be able to go lower than that, 48 megabytes. Debian Buster with the Debian OpenJDK 13 distribution, a custom runtime with that same Java-based modules, almost 500 megabytes. And there's no typo there. Why? Because the Debian OpenJDK builds include the native debugs information. Luckily for us, we have these new jlink flags in JDK 14 that we can use to strip out the native debug information. If you do that, you will have a custom Java runtime with the Java-based module that weight 51 megabytes. So you are not reaching the 48 megabytes that we have with Oracle OpenJDK build, but we are almost on parity. So if you are using such distribution, and if you are getting funky numbers, well, look at the native debug information. So we've talked about what we can do at the container level to reduce the startup time. Now let's look at the Java level. What can we do to improve the startup time? This slide shows the startup time of a simple Hello World application between Java 8 and 9. And clearly, smaller is better. So that clearly means that between 8 and 9, we had a big regression. And there is an easy trick to solve that regression. Basically, if you use the latest and greatest, there is an ongoing effort going around the startup time. And you see that between 8 and 14, well, we are, the startup time for that same code is basically more than twice as fast. So that's an advice. If you can, and if the startup time is important to you, try to use the latest version of the platform. This is basically the same slides, but so we have a Hello World application. We have a Hello World application that is using Lambda, and a Hello World application that is using concat strings. And basically, you see again and again that with each release, there is an ongoing effort to reduce the startup time. If you want to have more information about the startup time and Java performance in general, there is the blogs from Klaas, who works at Oracle in Stockholm, and is basically putting a lot of useful information about Java performance and startup time there. So I encourage you to check that one out. OK, something else that we can work to reduce the startup time of Java application is CDS. We can use class data sharing. Anybody is using CDS today? Anybody knows what CDS is? OK, 1-2%. It's a bit scary because CDS is in the platform since Java 5. So 15, 16, 17 years ago. So the basic idea of CDS is basically the following. When you start a Java application, so you have a bunch of class on disk, the JVM will have to load that and turn that into something that it can use to basically run your code. So you have a class with bytecode, and that bytecode will have to be scanned and parsed and checked and so on to basically be turned into something that the JVM can exploit. And the thing is that, obviously, with your Java application, you don't have one class. You have a bunch of classes. So that means that each time you start your application, you basically have to go through all those steps again and again. The idea with CDS is that it will only happen once. So you will start the JVM, and the JVM will basically do an in-memory snapshot of all the representation of your code in memory. It will dump that to disk. And the next time your Java application is started, it will bring directly that into memory, so that the JVM doesn't have to go through all those expensive operations on all the classes. So that's the basic idea with CDS. We have that in the platform since Java 5. It was pretty limited back then. It was only for the serial GC. It was only for the run. Back then, it was only for the runtime classes, so the rt.jar of Java 5. But CDS has been evolving since then. So let's have a quick demo of CDS in action to see what we can get. So let's see. Yes. So I have this Hello World application, same code. So this is my application. In this case, it doesn't run within the containers. So I'm going to compile that. And I'm going to use that. I'm going to invoke that application multiple times without and with CDS so that we can see what we get in terms of. So for that, I'm going to use perf42, which is basically just an alias that is invoking perf 42 times. Why 42? Because 42. So perf 42 Java. So hello world. So the first time I'm going to avoid CDS. So 42 times my application is invoked. And on average, it takes like 205 milliseconds. So let's do the same exercise, but with CDS this time. And to use CDS, it's pretty easy. We just have to use the default behavior. So 205, we can already see that it scrolls faster. So this is good. So from 205, we went to 135 milliseconds to invoke that Java application. So basically, oops, 35, whoops. We are like at 65% of the time with CDS than we are without CDS. So this is a huge benefit because it comes for free. That's something that the platform provides. So I told you that at the beginning, CDS was limited to the runtime classes, but now not anymore. That's something that we can also use for our own classes. So that's my CDS demo. Obviously, my application is pretty basic, so that's why I have a huge win. So don't take my words about the benefit of application CDS. So application CDS is basically for the class of the application itself. This is a quote from Gunnar from Red Hat, and on Quarkus, they are seeing a reduced startup time of 30% with app CDS. Another quote from Charles Nutter, who runs the JRuby project, and JRuby in itself is a huge project. That's the benefit that they are seeing with CDS. So just look at the bottom. So they go from 853 milliseconds to start up JRuby to 717 milliseconds with app CDS on a Java 13. So this is something that you should leverage. And that's something that we should also leverage when Java runs within containers, obviously. So I mentioned that CDS is not new, introduced in Java SE 5, but it has been evolving since then. So at the beginning, it was quite limited. So serial GC, only the system classes. Later on, in Java 9, we have introduced application CDS and support for additional GC. But back then, it was a commercial features of the Oracle JDK. So you basically had to pay to use it. Good news is that application CDS was open source in Java 10. So that's something that since Java 10, that's a feature that is part of the platform. In Java 12, we have introduced default CDS archive. So you don't have to create the archive, the runtime archive, if you will. In Java 13, we have introduced dynamic CDS archives. So before to create the archive, so basically the dump of your classes, you had to go through multiple steps. In Java 13, there is a flag. You just launch your application, and you will have the archive of your own classes created directly. So it's more convenient. And we are keeping improving CDS with all the release. So something else that we can also leverage to reduce the startup time of our Java code is to use GraalVM. GraalVM, it's an high-performance polyglot virtual machine developed by Oracle Labs. It provides many capabilities. On the Java side, two well-known capabilities is the JIT compiler. So it's basically a JIT compiler that can replace C2. One of the unique things of that JIT compiler is that it's written in Java, and you can plug it directly into a hotspot. They also have an AOT compiler in the form of a tool called Knative image. So the goal of the Knative image tool is basically you feed it with some Java application, and at the end of the day, the artifact that you will get out is an executable for a given target. So multiple reasons to do that. Reduce the startup time. So it's not a Java bytecode running on top of a Java virtual machine, but it's really a native executable. Improve footprint. So technically, your code running in that executable will consume less memory because it doesn't have the overhead of, for example, a JIT, those kind of things. And the side effect is also the reduced image size. So that's something that we're going to see. So let's see. For that, I'm going to go back to my Mac. Let's first see which Java version I have. So 13, let's switch to Graal. So one of the perks of working within version Shell. So yeah, one of the perks to work in the GPG group is that you need to deal with a lot of versions of Java on your machine. So I want the shell to use 11. OK, this is indeed, you can see that it's a GraalVM. So let's see. So I still have this Hello World Java application that I'm going to compile. And then I'm going to pass it to native image. So I'm going to pass the class to native image. Hello world class. So what's wrong? Found defunct image build server. That's a bit scary. Hello world class. Sorry? Oh, thank you. That's the keyboard. OK, so what it does, so wait, I think I have a slide. So. OK, so what I've done here, so I've passed my Java application. In this case, it was a simple classes to the native image. That's not the keyboard, that's the Mac. OK, so I've passed that to the native image tool that will basically look at all the reachable code path, and it will, at the end, compile that code into a native code. And what I will get at the end is a native executable. And if I go back here, so I should have a hello world. So if I look at that file, hello world, that's a Mac OS executable that I can obviously launch. So what it sees is a Java 11.05 version. And to prove you, so I'm going to switch back to, let's say, 14. Yeah. So my current Java JVM running on my Mac is Java 14. But if I do that, you'll see that it still sees the basically substrate VM, so the lightweight VM that has been embedded in that native executable. Something to mention is the size of that guy. So 8 megabytes. So in 8 megabytes, you have basically everything. So that's, well, there's no Java runtime because it's directly embedded within that executable, and your Java code itself. We can time the invocation, so 10 milliseconds, and we can compare that to the same code running on hotspot, so hello world.
Didn't run a command because it didn't find.
Sorry, you're right. Well, it won't be a lot. You see, 3 milliseconds. Yeah, we can compare that to, so let's see, Java. We can compare that to the same code, but this time running on top of hotspot. And, well, it's a bit slower. So let's see, 13 milliseconds and 151 milliseconds. So not only we have a smaller executable, but it starts way faster. Having said that, there are a few limitations with Graal. So right now, Graal only supports Java 8 and Java 11. There is this mostly supported branch that basically means that reflection, dynamic proxy, GNI, and so on works, but you have to do some configuration works to make it work, right? And then there are a few things that are not supported, such as invoke dynamics, dynamic class loading, unloading, and so on and so on. Now, the thing that you have to keep in mind is that with GraalVM native image, what you will have at the end of the day is a native executable. So you will not be able to use the typical tool that, like GMC, that you are using to, for example, observe your JVM. You will not be able to use the Java debugging tools that you are used to use, and so on and so on. And also, portability is kind of lost because if you want to deploy your code on multiple platform, you will have to compile for those different platforms. So there are a lot of benefits of using a native image, but there are also a few drawbacks. Something also that you don't have in a native image is you have a pretty basic GC, like a serial GC. So if you have long-running code, maybe you are better to leverage the hotspot GC, such as ZGC, and so on. So that's something that you need to keep in mind when you're using GraalVM. There are pros and cons, like hotspot, pros and cons, right? OK, let's switch to the last point that I want to address today, is about the fact that the JVM should behave correctly when it runs within a containers. So I'm not going to go into details about that slide, but basically this slide shows that we're making the right investment in OpenJDK to make sure that hotspot runs correctly when it runs within a JVM, when it runs within a containers. It's something that we have started since Java 8, and since then we have continued to do improvements. If you look at the bottom of the slide, there is an enhancement that has been merged 2 weeks ago. That's support for cgroups v2. If you are using Fedora 31, for example, that's something that you will need. And that's something that will land in JDK 15. So why it's important that the JVM behaves correctly and understand that it runs within a containers? Because of the JVM ergonomics. So since Java 8, we have this notion of ergonomics that basically, it's the ability that the JVM has to auto-tune itself. So the JVM will look at a few metrics, basically the memory that it has access to, and the number of CPU that it has access to. And based on those two metrics, it will configure the JVM so that you have a good default out-of-the-box behavior. So it will pick a GC that is appropriate. It will set the heap size, and the JIT compiler to use based on those criteria. So let's have a look at why this is important. Let's see. No, sorry, I was on the... So for that, I'm going to use the image that I started with. OK, so this is the image, the Hello World application that we did at the beginning of the presentation. So this one sees that it has 8 CPUs, so the JVM configured the command for join pool to use 8 threads. The runtime max memory is also configured based on the available memory and the max RAM percentage flags that is 25% by default. So let's see. So this VM has 8 CPU. So that's why the JVM sees 8 CPU, and hence we have 7 threads. So now what I'm going to do, I'm going to basically say that my JVM, so my container can only use 6 CPU out of the 8 that my VM has. And what we can see is that, well, the JVM still sees 8 CPU, and hence it's configured to use 7 threads. And I could go down up to 1 CPU, and it still sees 8 CPU. Why? Because, well, I'm using, in that particular case, I'm using a very old Java version that is not container aware. So that's something that you want to avoid. And I'm going to show you that. Let's see. So I'm going to use this one. Let's see. So this command runs OpenJDK. So by default, it's 13. Within OpenJDK with the Java command, we print all the flags, and I explicitly disable container support, because container support is enabled by default. And let's see. So you see that in this case, I have a JVM OpenJDK 13, 1 CPU, and the default GC that is configured is G1 GC. Clearly, that's not going to work. Why? Why? Because this JVM is not container aware. Now, if I if I take the default behavior, you will see that now, so my JVM has 64 megabytes of memory and 1 CPU, and you see that G1GC is not used anymore. So now it will behave correctly. So with 1 CPU, it's better to use serial GC instead of G1GC. So that's the kind of trick that JVM does. But for doing that, we need to make sure that it can seize the right metrics. That's why we need to make sure that we are using a JVM that is container aware. So this is true for the GC that is used, the memory, and basically everything that is based on those metrics. So for example, this container has only access to 64 megabytes of memory. If I disable the container support, or if I'm using an old version of Java, the JVM will basically seize the memory of the host, like 32 gigabytes. And clearly, it will very quickly overconsume memory, and it will basically be killed by the container runtime. So let's see. Yes, it's time to wrap up. So JVM containers, that's what we have discussed today. We have discussed about techniques that we can use to reduce the latency, so basically improving the startup time of the container itself, shrinking the layers at different levels, using jlink, for example, using Alpine. And then we also discussed at some of the techniques that we can use on the Java side to improve the startup time of the JVM and the Java code. And clearly, those techniques can also be used outside of containers. We've then discussed about why it's important that the JVM behaves correctly when it runs within containers. We saw that it's important to give the right metrics to the JVM ergonomics to make sure that it's not killed by the container runtime itself. So please use the latest Java version, and please never use Java latest as I did at the beginning. That image is very old. It's not container aware. That's an image that you can only use when you're on stage and you are doing a demo in front of a bunch of people. Don't use that in production. I also use container support flag. You don't have to, because if you are using a recent version of Java, it's enabled by default. That's a flag that you will only use to explicitly disable the container support. And I'm not sure that you want to do that unless you want to do demo like I do. If you cannot use the latest Java version, at least rely on an actively supported Java version to make sure that it is container aware. And don't use a JDK to run your Java code within a container, but please use a JRE or a Java runtime. And we saw that using jlink, we can create custom runtime images that basically fit our needs. And for the rest, it's really container as usual. So you can use all the tools in the container space, and so on and so on. So I'm going to conclude with this. The top 10 most popular Docker containers contain at least 30 vulnerabilities. The good news, Java is not there. The bad news is that we are not immune. This was back in May, where Debian basically shipped an OpenJDK build GA before it was even GA on the OpenJDK community. I mean, it's easy. Everything is open source, so the source is there. So someone took the source, built it, and tagged as GA. So watch out. Something else that I saw last week. There's no OpenJDK 11 Alpine build for Alpine. But someone on the internet said that, OK, that build is pretty close to what it should have been if it would have been GA. So you can consider it as the OpenJDK 11 Alpine GA release. There's no such a thing. The problem is that many people now rely on that pseudo GA release. And then when you deep dive, and if you look at the Docker file, you realize that basically it gets over HTTP from a university in Austria, a build. The good news is that they're checking the checksum. The bad news is that they're checking the checksum from that same host. So basically, you get a random build that a lot of people are using, and it's clearly not an OpenJDK 11 build for Alpine. It's something that will work, but we don't know what's inside. So please choose your base image wisely. Also choose your OpenJDK distribution wisely, and secure it. And don't trust someone else to secure your base image. Don't trust someone else to choose your OpenJDK build. And don't trust what you read on the internet. With that, I'd like to, yeah, there is one which is very secure. You see? Don't trust someone else to secure it. That one is very secure. You see? So, thank you.